Okay, everyone. I wanted to take a little bit of time and do a quick video on IR spectra, another video on IR spectra. And I've got this special piece of software that you're looking at right now on the screen. This runs on my PC in my office, and it basically allows me to build models and then find out what the structures of molecules are, and it allows me to do a bunch of other things as well. But what you're looking at here is a model of acetone. So you can see that we have three carbons, six hydrogens, and a carbonyl, right? The carbon double bound to oxygen there. And so this looks exactly, pretty much so like what you would have if you had a ball and stick model kit, or look very closely like the what it would look like if you built a model using your model kit that we use for the class. Now, the cool thing about this particular piece of software is that it allows me to actually calculate not only structure but also spectra like IR spectra and other spectra that we'll be talking about later. And so I want to really show you kind of like what some of these stretches and things that we've been talking about actually look like. Now, this is a calculated spectrum, and actually does not line up terribly well with the experimental spectrum because I'm using a very low level of theory to make these calculations, because high levels of theory require a lot of computer time that we just don't have. But nonetheless, it'll give you a very accurate representation of what the stretches actually look like. So if you will right now go get your model kit and build a structure of acetone that's right here. So three carbons and a carbon oxygen double bond, right? As part of those three carbons, you'll have the structure of acetone. And what you'll notice is that the bonds are rigid. They don't move, they don't vibrate. So our model kits are actually not very good models for this type of thing. But nonetheless, I can do it in the computer. And so I want to show you what some of these stretches are. So for example, you see this really strong stretch at around just under 2,000. So it's between the 1500 and 2000. So it's an sp2 hybridized carbon that's actually the carbonyl, right? And if we click on that, it'll show you what the stretching actually looks like that gives rise to this stretch. If I can get it clicked on, I'm doing this through. There we go. That is what that particular carbonyl stretch is looking like. And what you can see is that the carbon-oxygen double bond is stretching, and that actually changes the dipole moment of the molecule. Okay, now I've got this table over here. I can turn on and turn off any type of stretch that I want. Now let's look at something in the hydrogen region. So what we notice over here in the hydrogen region at 3,000 and above, we can see that there are actually quite a few different stretches that we can look at. So let's take a look at this one at 3199. So the hydrogens are actually vibrating that way. If we look at the one at 3206, it's a little different type of hydrogen stretching. 3249. Okay, there are all kinds of possibilities for stretching those hydrogens. They're not all the same type of stretch. And so it can get quite complicated, actually. Okay, kind of funny, right? Looking at all these little stretches. But we can also look at some of these stretches in the fingerprint region. So these that would be below 1500. So let's just pick on one. Let's say we take this one at 1315. And what you can see is that's a kind of a wag, if you will, right? So this molecule is wagging. And it's not a stretch of the carbon-oxygen double bond. And that's why it appears in the fingerprint region, because it's the stretches of these bonds here that are sigma bonds. Now let's look at some others. Let's just pick this on this one at 1201. It's kind of a bending stretch. We've got kind of these hydrogens doing this kind of business. 981, it's kind of this rocking motion. 806, the bond stretching like that. So you can see why all of a sudden the fingerprint region gets really complicated and doesn't tell us a whole lot about the functional groups. Tells us a lot of information, but not a lot of useful information for this particular course that we're interested in this semester and next semester, to be quite honest about it. We were going to use IR spectra to basically tell us what the functional group is. And right now the functional group, right, is this carbon-oxygen double bond, and that happens to be that particular frequency. Okay, so I just wanted to spend a little bit of time and actually show you that you can model these things in the computer, and that we can build all kinds of models in the computer just like we can with our model kits. You know, you paid $30, $40, whatever it was, for your model kit. You get to hold that in your hand. You get to feel the model. You get to feel the molecule. You get to see how bonds rotate. It works really well for that. But beyond that, you really need something more sophisticated, like what I have here with this program called Spartan. And I have the professional version of Spartan, and Spartan costs about $2,000. And so that's why we don't have you all buy this professional version of Spartan that can do all these high-level calculations. So I wish you all a good holiday weekend. Spend a little bit of time studying your organic chemistry. Don't let it get rusty before Wednesday. And don't forget, your inverted lecture will be due in class on Wednesday when we get back.